The objective today is to explain what the Intel manual says about random data types. This is my own language here because part 26 will just cover quite a few of these. So the first one is a bit field data type, and it says a bit field is a contiguous sequence of bits. It can begin at any position of any byte in memory and can contain up to 32 bits. Alright, so I'm thinking of really small numbers when I'm thinking of a bit field. It seems odd that we will break bytes down into the bit level. So the first question is, what is a bit field? You can answer that by just saying it's a data type, or you could be more specific and say it is a data type that basically breaks down a byte into however many bits it needs to. And I'm sure you're familiar with the concept of a least significant bit, or at least the least significant byte in Little Endian. If I'm correct, I heard that the least significant bit will always be on the right-hand side when we're talking about the bit level. But I suppose the point I'm trying to make is when we're talking bit field data types, the least significant bit will be over here, and we can be looking at like a 3 or 4 or 6 bit field of numbers. Alright, so if we go down here, the next random data type is strings. A lot of you are probably familiar with strings. Strings are continuous sequences of bits, bytes, words, or double words, and a bit string can begin at any position of any byte and can contain up to 2 to the 32nd minus 1 bits. A byte string can contain bytes, words, or double words and can range from 0 to 232 minus 1 bytes. That is to say, like 4 gigabytes. And that's a lot, so I'm kind of thinking of like not just a single novel or book, but mini books. Or maybe like this Intel manual, which this one is 482 pages, but I've seen ones of 1400 pages. But what these byte strings and bit strings are supposed to be holding is strings, letters or characters that are combined to make words. And apparently these need to be continuous, which makes sense. If you've ever seen a hex dump, you understand how there's this continuity. Well, the next data type is called a packed SIMD. SIMD stands for Single Instruction Multiple Data. Alright, and I actually did 2 questions here, so let's make sure to say what a bit string is, maybe even mention how that's different than a byte string, and then say what does SIMD stand for. Maybe the perfect example of a bit string, since it can go up to 32 bits, would be the idea of like there's these ASCII encodings where every letter is 8 bits. Well, technically 7 bits, but it's stored as an 8-bit number. And then you have Unicode, and then you have UTF-8. These are all similar encodings because they're just letters being encoded. But Unicode is using 2 bytes if I remember correctly. So I imagine that could be considered a bit string, maybe a byte string, a 2-byte string, or a 16-bit string. I wonder how that works. I'm sorry if you came here to learn and all you do is end up leaving with more questions. I guess this section will just require us to do a lot of additional research. But this video series will just focus on the Intel manual, so we'll all do that additional research another time. Maybe watch out for those videos. So this SIMD paragraph says that Intel 64 and 32 architectures define and operate on a set of 64-bit and 128-bit packed data type for use in SIMD operations. These data types consist of fundamental data types, such as, the words, double words, these things we've learned about, and numeric interpretations of fundamental types of use in packed integer and packed floating point operations. So maybe a good question is just like, what is packed referring to? And looking ahead, it looks like this diagram will go ahead and help us with that. But let me read the paragraph first. The 64-bit packed SIMD data types were introduced in the 32 architecture in the Intel MMX technology. They are operated on in MMX registers. And the fundamental 64-bit packed data types are packed bytes, words, double words, etc. When performing numeric SIMD operations on these data types are interpreted as containing byte, word, or double word integer values. So cool visual to go with that paragraph. Maybe packed bytes means we can access each individual byte. If it's a packed word or a series of bytes that are called packed words, we can access them 2 bytes at a time only. Might make sense in that Unicode example. Or we could pack double words together so you're only allowed to access a double word at a time. Nothing smaller in that sense. And thank goodness, I mean, that's really the same for whether we're in 32 or 64-bit mode. Though that's not what these titles say. This says 64 packed integer data types, and this says fundamental 64 packed SIMD data types. So the way they handle data and integers is the same. Well, the last paragraph on this page, 94, says that the 128-bit packed SIMD data types were introduced into the IA32 architectures and the SSE extensions. This just means that they added, I think sometime in the 90s, Intel added more instructions we could use. So it was introduced when Intel did that, adding instructions to the processor, and it used these extensions. They are operated on primarily in the 128-bit XMM registers and memory. The fundamental 128-bit packed data types are packed bytes, words, double words, and quad words. When performing SIMD operations on these fundamental data types and XMM registers, these data types are interpreted as containing packed or scalar single precision floating point or double precision floating point values. So a nifty diagram to help us finish our lesson, because part 27 will go ahead and go into this binary coded decimal integers. But in our diagram here, they just show us the same thing basically. So I'll just ask the question, when do programs use 128-bit packed SIMD data types? Because this is very new to me. But I mean, the concept of using integers is definitely not new, so that's why I created that question. I hope you're a little more comfortable with all the random data types the Intel manual throws at us at this section, and in the next one we'll go ahead and go into this binary coded decimal integers.